Good afternoon, everyone. It is a huge pleasure for me, Ken Goldberg, to introduce our speaker today. He is one of the major towering figures in the field of robotics, and Peter Abiel and I have followed his career closely, and were thrilled when he accepted the invitation to speak in the Bair Distinguished Lecture in Place series. He has a distinguished career from his undergraduate at the University of Michigan, and did some work in neuroscience, and then moved to MIT, where he has done pioneering work on legged locomotion, on fixed wing UAVs. He has established a stellar reputation in applying rigorous theory to robotics. He has a particular emphasis on applying stochastics and optimization systems theory to very difficult problems in the field of robotics and now automation. He is now the full professor, the Toyota professor of computer science at MIT. He also has appointments in mechanical engineering, Astro Aero. He is a member of the CSAIL group, and he also has a position as vice president of research at Toyota Research Institute. He has received a huge spectrum of awards. He has the NSF Career Award, the MIT Jerome Salter Award for undergraduate teaching, DARPA Young Faculty Award in mathematics, and I could go on. We won't dwell on this, as well as a number of best paper awards. His work on Atlas, in particular, Little Dog, is world renowned. His perching flying robot is etched in everyone's memory. He has done work on whole body planning, and is also pioneering an exciting simulator, the Drake simulator. And he has recently turned his attention to manipulation. And people like myself and Peter are extremely thrilled about this, because now he's taking on some really hard problems for a change. So we're going to hear about what he's going to say today, and I think we have a huge audience here, over 200 people, and I'll turn it over to you, Russ. Thank you so much.
Thank you, Ken and Peter. Ken, that was a great introduction. I appreciate it. It set me up well, because indeed, I have been working on feedback control for a long time. Let me just actually, before I start, there's a URL at the top of my slides. Hopefully you don't have to type that in. It'll be in the chat also. But if you open it there, you can watch the slides traditional Zoom, but if you open it there, you'll get to follow along with me in your browser. And for someone who works hard on robot videos, it kind of breaks my heart to play them over Zoom at decreased frame rate. If you watch them in your slides, you'll get to see the full experience, and there might even be a few interactions here and there. Okay, so it would download directly to your browser. Please click on that, you'll get the better experience. Okay, so yeah, I've been working on feedback control for a while, and my first full frame rate video, hopefully, is, oops, click on that, is, as Ken said, I worked a lot on a humanoid robot for the DARPA Robotics Challenge a few years ago. This was the 400-pound Atlas robot built by Boston Dynamics, but we had to program it to drive that car, open the doors, walk around, turn valves, pick up drills, walk over rough terrain, climb up stairs. This was a life-changing experience for me, partly because it was completely exhausting and then stressful, but it actually really cemented a lot of, it sort of helped me define my thinking about these problems. One of the, a big part of that actually was, again, feedback control. So, I got to see mathematical systems theory, applied to a pretty complicated system, and it just worked incredibly well. This was the time where this was a practice session, but DARPA set us up to have a 400-pound humanoid, but also set us up to have a pretty little car we had to get out of. So one of the hardest parts of the competition was just getting that robot out of the car. But we had a balancing control that we really loved and trust, and that was running a quadratic programming optimization at every time step. This was using optimization-based control to really make a big hardware system work. Okay, I want that now for manipulation. I've turned my attention to manipulation, and much to my chagrin, we don't have the same, the mathematical control that I know and love, the algorithmic control I know and love. This algorithm, for instance, doesn't work for manipulation the way it works for this humanoid. And I want to talk a little bit today about why and how and maybe what we can do about it. So just to be clear, when I talk about feedback control for manipulation, I don't mean feedback control of the arm. That's something that we've known how to do for a long time. We can move arms around using feedback control in factory room floors. That's not what I mean. The interesting part is, how do you use the robot to control the state of the environment? You measure the state of the environment, potentially with cameras, potentially with your tactile sensors or force sensors, and you're trying to control the state of the environment. In this case, it's a little red brick that the robot has picked up. It's the brick that I want to control, not the robot. And somehow that doesn't seem that much harder. It doesn't seem as hard as balancing a humanoid, but it breaks a lot of math. So let's talk about it. The other thing is, I don't want to just move bricks around, and it's important to me that we define manipulation as more than pick and place. There's a super valuable thing in manipulation, which is picking objects up, putting them in a bin. That's a very valuable and potentially profitable enterprise, but humans do amazing manipulation, and this is my goal, is I want to understand the dynamics of control of the type of manipulation that people do naturally and all the time, right? So tying your shoelaces is one great example. Buttoning a shirt is another great example. Spreading peanut butter on toast is another great example. We do all kinds of crazy things which are very far from pick and place, but squarely in the domain of manipulation. Okay, so how important is feedback anyway? I think it's reasonable to ask, actually, do we need feedback to be successful in manipulation? Or how central is it? And there's an alternative, right? You can have systems which are sort of passive, open loop, do the right thing. I can have a very smart planner such that even if I don't have any feedback, if I execute a trajectory open loop, then everything falls into place. A caging grasp is a good example of that. If I get my hand around an object and I move forward, then the object will actually tend to fall into the palm of my hand. That's a good example. There's also a wave of very clever mechanical designs that have happened in robotics. So these are these under-actuated hands. This is the one from Soft Robotics and just outside of Boston. And these things can pick up almost anything, right? So what's the problem? Maybe we don't need feedback control after all. This is just open loop commands. Well, it'd be hard for me to button my shirt or tie my shoes, I think, with some of these hands. So these hands are extremely good at some range of tasks, but I don't think they capture the diversity of manipulation that humans are capable of. Okay, so, if you watch, you really watch and introspect and think about what you're doing all the time, I actually think you're gonna find a lot of feedback in manipulation. This is high-speed footage of a person randomly in the convenience store, but if you watch for the little nuances. She misses the dentine gum, and then there is corrective maneuvers, and it's those little bits of feedback that are happening, I think, all the time when we're loading the dishes, when we're getting dressed, okay? And that's a layer of robustness and security that we should have for our systems, but we don't have a mature understanding of that yet for manipulation. Here's another just great example. You just have to watch yourself, and I think if you really can understand, it's kind of below our level of consciousness, but if you understand all the amazing things you do with your hands, I think you'll see lots and lots of places where it wasn't just relying on simple, open loop, stable solutions. Okay, you might say, feedback for manipulation is good, but it's already solved. We know, we've seen examples. OpenAI's example is awesome. I mean, I really think this is just a great project. It showed us that things were possible that a lot of us didn't think were possible. And it offers a recipe that I think we could believe in, which is first you have to make the simulator. Then you write your cost function. I almost wrote reward function, but I stuck to my roots here and wrote cost function, okay? And then you apply deep policy gradient. And maybe that's enough. Maybe we're seeing examples where deep policy gradient is is able to find complex, deep policies that perform surprisingly well. And that search space, I would think, is extremely nonlinear, non-convex, but these optimization systems do seem to work. But this isn't a magic solution yet, right? So every one of those steps is pretty hard. Making the simulator is already hard. Writing the cost function, we're going to talk more about that, but I think it's not always easy to understand how to write the cost function, right? If you want to have a robot load the dishes, how do you tell them, you put the robot in front of a dirty sink. If you just show it a picture of a clean sink, it's not, I would not know what that robot would do. Dishes might go flying. Maybe it gets the sink clean, but I think it's non-trivial actually to specify these cost functions. And then the deep policy gradient took a lot of compute. And I think, control offers a different level of maturity, I guess. The experience we had with programming Atlas, which was the Boston Dynamics humanoid, the 400-pound humanoid, and we spent a long time on the controller, made it work very well. But one of the hallmarks of, let's say, a more model-based, but also maybe just a more mature control solution is NASA sent us their humanoid. This is called Valkyrie. And within 3 hours, Atlas's walking controller was working to balance Valkyrie, and Lucas was pushing into Valkyrie with a 6-foot pole. So that's very compelling to be able to change tasks, change robots so quickly. I want that for manipulation. This is the plane landing on a perch that Ken mentioned quickly. This is a pretty complicated nonlinear controls problem, but we not only had a controller that we could generate that would work, it generated it in less than a minute of computation, in another, actually less than a second of computation probably to make the initial controller, about a minute of computation to provide mathematical certificates that could actually say exactly when the system was going to work, when it wasn't going to work, whether the wind was going to blow it off course or whatever. And that's still a pretty complicated system. So can we bring some of this maturity to the field of manipulation? There's lots of reasons why it's proven to be hard so far. I like to talk about all of them. So one of my biggest focuses has been on control through contact and the implications of having even rigid contact and what that does to a control problem. For some of the dexterity you saw, for instance, picking the plasticware out of the bins, that's a very dexterous multi-contact task, and we don't have good solutions yet. Even if you give me a perfect simulator, the OpenAI is a good example, but I think that problem is still hard. Tactile sensing, and along with it, changing the mechanics of contact. I'll mention that a little bit at the end today, if I have time. Distributional robustness. It's not enough for me to say, I want the controller to work in one experiment in the lab. I'd like to try to understand how to build robustness into our manipulation system so that I could deploy it to anybody's kitchen anywhere in the United States or across the world, for instance. That's really, really hard. In control theory, we tend to think about polytopic uncertainty sets or ellipsoidal sets or Gaussians or whatever. I don't think my kitchen's a Gaussian distribution away from Peter's kitchen. And also I think the skills that we're talking about have to be layered into complex scenarios and tasks and composed in different ways. It's probably not enough to learn one narrow skill if you want to build a general purpose manipulator. But I have to pick, and I was thinking about how many interesting people could potentially be on the call here, and it's fun to think about that actually. And so I had to pick something, and I thought I'd dig in a little bit more about thinking about the challenge of doing feedback from cameras, and in particular, some of the issues that come up in state representations, which are really occupying a big part of my brain these days. Okay, so just to be clear, I want to sort of labor the point here, but this is, ironically, this is one of the interactive animations. If you care to zoom around or anything on your browser, you're welcome to. But let me just make the point very clearly about state representation. So I told you the problem here is to control the state of the brick, in this case, the object in the world. Of course, there's a natural state representation, which is the I could think of the state of the robot as parameterized by the joint angles, and I could think of the state of the brick parameterized by the 6 degree of freedom representation of the position and orientation of that brick, an SE3 pose, right? If the velocities, if the inertial effects matter, then I have to go to a second order model. Maybe the velocities come into my state space. But Lagrangian mechanics gives me a very natural state representation for this problem. So that's not what I'm talking about. I'm not talking about the difference between, Euler angles and quaternions or anything like that. Those are good problems. But I'm thinking about, take those control ideas and apply them instead to something like this. And this is, when I think about the state space of this, with my control theory hat on, it almost melts my brain, right? So every time one of these knives comes down, I'm getting more state dimensions. Do I really have to track the pose of every piece of the onion? And do I have to worry about the contact mechanics between all the pieces and each other in order to solve the problem? Probably not. Probably at some point it becomes a pile of stuff. And this is just one example of many. I think, buttoning my shirt or buttering toast, these are all good examples. And I have to admit, they break my tools that started with Lagrangian mechanics, because that's just not the right representation for the problem. So that one does kind of melt my brain. We were trying to think of something that was maybe a step from the brick towards that bigger state representation problem. And I found sort of a sweet spot here in the first step here of doing category level manipulation. So I want to land that story first, and we'll get back to the onion in a little bit. So it already breaks my representations a bit if I ask simply, do something with every mug. Okay, so if I have just a single mug and I've only got one mug or one CAD model for a particular mug, then I can think about its pose as its representation. But if I have to do the same task, specify the task even, let alone design a feedback controller for the task, to work for every mug, that actually already, it doesn't sound like that big of an advance, but that already sort of challenges the representations we had been using. And so let me tell you first about this idea of using key points as a representation. So the task was, again, it's category level. We didn't just do mugs. We also tried to be able to manipulate any shoe. Now, both the shoe task and the mug task I just showed you, it's important that they weren't just picking it up and dropping it somewhere. They had to have enough understanding to do something meaningful with that. So in the first case, the mug had to hang itself by the handle on the rung. And in this case, the toe of the shoe has to be pointing forward. So it's not enough to just think about the geometry. You somehow have to understand a little bit more about the shoe. Okay, so here's the problem, is to manipulate a potentially unknown rigid objects, but drawn from some category, loosely defined. I wish I could make it more precise, but not today here, into some desired target configuration. So we'd like to somehow specify a potentially precision task, but have it work for every mug. And it takes a minute to think about it, but actually the temptation to use just the position and orientation on some canonical frame on the shoe or the mug, it seems natural, but if you think about it, it's not enough to solve these tasks. It's very hard to put a canonical frame, especially that stays relevant to all of the tasks on any one of these objects. So when that disappears, then we run into this problem of how do we even specify the task? So what's the cost function, right? Do I just put an image of the mug on the rack and hope for the best? It turns out the key points provide a simpler solution. So the perception community has been making incredible use of key points over the last few years. They provide a rich class general semantics, and it turns out they work really well in our manipulation pipeline. So in practice, we can train networks to look at an image, predict the location of a handful of key points, and then we can write costs and constraints on those key points to transform those key points, assuming they stay rigidly attached, into some target configuration. That turns out to be a simple idea, but a very nice one that works in practice. It happens to fit right into our sort of optimization-based planning pipelines. So we have, for a long time, been thinking about kinematics as an optimization problem. So if we want the robot to put its hand in a certain place, we can say, not just put your hand in a certain place, but actually find the best, most comfortable configuration, for instance, subject to your hand being a certain place, but you've also got joint limits. You might be avoiding collisions. You might have to keep your hand in the field of view of your cameras. You probably don't want to fall down, okay? All of these things actually map very nicely to the problem of specifying with key points. In key points, another thing you can do with optimization is you can specify a manifold of solutions. So you like your hand to be parallel to some surface, or you'd like the points of the mug, for instance, to be in some under constrained configuration. The solvers work well with that. But key points are not a sufficient representation by themselves. We combine key point semantics, the idea that this is the toe of the shoe, this is the tongue of the shoe, this is the heel of the shoe. That's the key points are giving us that. But then we have to combine that on the fly with dense 3D geometry in order to do the actual task. So from a point cloud and some online dense reconstruction, we get enough, enough information to know where to grasp. And then once we have a grasp, we can transform. We can assume the object is rigidly constrained to the hand, and we transform the hand in order to transform the key points. And this is something that we really hammered on. And you could go into the lab, before March, and take off your shoe and put it on the rack. And very rarely did we find a shoe that would stump us. And when we did, we just added it to the data set, and life was good. So, it turns out you can find a lot of pretty strange mugs on Amazon, and we did some pretty hard testing on it, and I was quite impressed with the performance. You can combine it with things like shape completion to do even more, to infer the geometry that you couldn't see from an immediate view from your cameras, and that worked well to, for instance, add collision avoidance constraints to the object as it's moving. Okay, so the key points are a different option for state representation than the pose, okay? They're connected to geometry, of course, but we are also using them for something different. We're labeling the semantic points on the object, the tongue of the shoe, the toe of the shoe, for instance. But those required human labels. So I think we want a little bit better. If we give up on the semantics for a minute, can we self-supervise and get the same kind of key point pipeline working to do maybe a more self-supervised autonomous state representation? And we've made a lot of progress on this. The first core technology is this idea of using dense correspondences. So this is a type of image I'm going to show you a handful of times. Let me make sure it lands. On the left is a picture of the hat that's still. On the right, in the center and on the right, is a video of an ongoing experiment. And there's a mouse over the green circle is on a particular point on the hat. And then in the middle is the heat map, which is the output of the network on what it thinks is the likely location of that key point, effectively. And on the right is a correspondence function that we've now used to try to find roughly the maximum likelihood key point, okay? So what you're seeing here is the correspondence. If you convince yourselves that from the left to the right, in different scenes, from different views, the system's able to correspond a similar point on the hat with the left to the right, then we've done our job, okay? And it turns out that works pretty well. And the cool thing is about it it's self-supervised. So we have the robot just waves its camera around, builds a dense 3 construction, basically SLAM for roboticists. It's simultaneous localization and mapping, but these are good, strong algorithms that you can that are sort of commodity algorithms almost at this point. Then we use that data to correspond the points from our mesh back to all the images that it took. And so you can basically say in this frame and in this frame, we know that this is the same point, and all the other points should not be called the same. So it's a pixel-wise contrastive loss. So here's again the same kind of image. This time we're showing, for those of you that have followed any work on dense object nets, things have gotten a lot better lately. Originally the heat maps were kind of broad, and we've been able to train them much better now, and they're much sharper. The correspondences are quite precise. Here's the crazy thing that we don't really understand, but we've exploited, is that somehow if you train the system on one hat at a time, and a variety of hats, something about the representational power, or there's something about efficiency, but it chooses to use the same dense descriptors for different objects of the same class. Okay, so turns out I can do correspondences across objects at the class general level, which is sort of amazing. Okay, but we've been able to exploit that property. So can we use those dense descriptors as self-supervised key points? I mean, to some extent they are, but the problem is there's a lot of them, and a lot of our pipelines before assumed a sort of sparse set of key points. And then without semantics, how do we even specify the task? Okay, so the way we did it in the first version was once we have our scan, we can just click somewhere on the object, ask, now for correspondences with that object, and you can do some manipulation tasks like pick up the object. You want to pick up the object from the same point every time? That's already enabled by this representation. But we wanted to do more. We wanted to get to the feedback control problem here. So can we use dense object nets in a feedback loop? And so Sergey and Chelsea and Trevor and Peter did some amazing work on visual motor policies, and we tried to build directly on top of that. So this is sort of pixels to torques is our favorite words for it, right? So going from a camera image and the state of the robot directly to an action, some lower level action on the robot. But if you look at the way that those systems are typically architected, it's actually, there's one big network up here that takes the image and brings it to some low dimensional feature representation, 32 in the first versions of the paper, and then brings in the robot's representation, the 13 degrees of freedom, so to say, of the robot, and there's a relatively small policy then that does the control. So in fact, it's nice to do this because then you can pre-train your image on massive image data and then have relatively simpler training procedure for your policy. And there were a number of ways to train these in prior work, using a loss based on trying to reconstruct a pose, doing autoencoders, sometimes even training end-to-end. But the proposal here is, can we use a small set of those descriptors as our small output from perception in order to put that into a policy that we can learn efficiently? Okay, so we had dense descriptors so far. What we're going to do here is we're going to pick in the descriptor space, which I didn't explain carefully, but the descriptors map from an image in RGB into some d-dimensional space of descriptors, okay? And we're going to pick just random points in that descriptor space, and only a small number of them, okay? And use the correspondence between those random points in dense descriptor space as our representation for the policy. Okay, so before we could do the full feedback synthesis, we started with a simpler problem of just imitation learning. And it's not just because the control problem's hard, it's because this is getting to the, how do you even specify the task? So imitation learning gets around all that. We're gonna give demonstrations of what those key points do over time. And we do that both in simulation and on the real robot. And then we clone the policy from Pete, who's on the robot, into the policy, and we see whether we can get good performance out. The simulation experiments were very promising. Even with a small LSTM network, with about 100 LSTMs, we were able to get pretty robust performance for some of the standard sort of box pushing tasks, but even some of the slightly less standard tasks. But what sort of blew my mind was the performance in reality. So for a pretty diverse set of, albeit simple experiments, this system was able to produce extremely robust performance. It's the thing that we were looking for. It's the thing that I think others here on the call have experienced this too. It's the thing I experienced on Atlas. We got back to this place where the manipulation system in this case was robust. You'd push it, it would respond, it would get the job done no matter what. And again, the core under there was tracking these dense correspondences even during, I mean, this is a pretty non-trivial task in my rigid body mechanics head. This is a deformable hat, okay? So the fact that it's working well for that and being robust is awesome. I put this up just to say we did a lot of experiments about it. The takeaway there, by the way, is that, I mean, this is just a cartoon really, but if you ask Pete or Lucas, how well does it work? I think their answer would be, there's kind of a set of places where we've given training data, and this is a high dimensional thing projected onto a two-dimensional plot, but their intuition was if you put the robot in a situation close to the training data, which is on the order of 100 demonstrations, then it works very well. And if you leave the convex hull of those demonstrations, no telling what's going to happen. This is my favorite of the examples, and it's I'll belabor it a little bit here. So this is just picking up a plate. It's a pretty non-trivial task. That's actually an unstable push because the plate tends to want to slide off to the side. But the visual robustness of it was impressive to me, and the mechanical robustness also. I mean, there's no detailed model of the plate. There's definitely no detailed model of the silverware and the glasses and the everything. So it still worked surprisingly well. Okay, but I'm not happy. I mean, I'm happy, but I'm not very happy with this. This is like an example that we can see great benefits from doing vision-based feedback in manipulation, but the imitation learning is a pain point, and we want something better. That task actually was inspired by we have this dish loading robot at Toyota Research Institute. And this is one of the most interesting tasks it does all day long, trying to load the dishwasher. It does these pretty nuanced behaviors of picking up the plate, and even if it's in a cluttered sink. And that was originally a handwritten solution by Siwan here. And actually, despite all the success we've seen with the maybe more learning approaches, we don't have anything yet that works as well as Siwan's controller. And his controller is like 6 lines and it has like 3 if statements. And I don't know, time after time I've seen very simple controllers being written by, I like to call them robot whisperers, that solve these really complicated contact tasks with state machine type logic. You see them from the Boston Dynamics videos, you see them from lots of different examples. And I'm still looking for that. That's not what's coming out of the deep networks yet. The cool thing is this has become, sort of a passion. We're hammering on this problem. I've been winnowing it down to sort of a textbook example. We can write a version of it with enough simplifications that you can solve as a POM-DP. We can hammer on it with policy gradient. We can ask all the questions. And in fact, if you were to have a conversation with me about almost any topic, there's reasonable odds I would probably say something about point fingers and a distribution over plates, because that's just what we're talking about a lot these days. And I think it's a good, a little bit harder than what we had been doing before, captures some of the distributional robustness, contact mechanics, and we should understand it well. Okay, but those demonstrations were a pain point. So can we do better? So less demonstrations and more generalization. So the next and the final piece of this story from Pete and Lucas's theses was to use those same dense object nuts representations to see if we could do it for online model predictive control. Okay, so the idea now is instead of cloning the policy directly from imitations, you'd use imitation data to learn the dynamics of the key point. So we're going to learn a deep network that predicts how the key points are going to evolve from key points in, robot command in, key points out, okay? And then use that in a planning loop to try to do model predictive control and execute a wider range of tasks. And the results were pretty awesome, especially since poor Lucas, this happened right when COVID hit and he couldn't get in the lab. So he got like days in the lab and got these things to work. And I think more would have happened if we hadn't been so constrained. But But there was an important takeaway for me on that last set of experiments, okay? The high-level summary for me was that we can train a network to predict the key point dynamics, even for very complex tasks, the hat with the deformable hat on a rack. But the planning and control problem is still hard. The reason that video is only of the box and not the hats and not the other things is because once I have this deep representation, we don't have a reliable, we talk to other people who may or may not have them, but we don't have a planning solution that I consider robust to solve that problem. It was interesting, Lucas at his defense, and he's sort of a conservative guy, but he says, perception doesn't feel like the bottleneck anymore. It feels like the bottleneck is control again. He actually said again. So, that's an interesting place to be if that's true. Okay. Sergey and I keep getting put into these situations where we're supposed to talk about deep models versus F equals MA, and this sort of I think this problem experiment speaks to that, which is, well, frankly, I don't think either of these deep models nor F equals MA is getting the job done for manipulation yet. But I also think the reason I think deep models aren't getting it done yet is because there's too much complexity still in the model. And I think I long for simpler models to come out, right? A joke I have with my students now is I said, if Newton and Galileo were to have deep learning, and they did a bunch of experiments and they shared the weights of their deep network, maybe even the architecture with us, where would we be as a society? There's something better, I think. Having prediction from a model is awesome, but it's maybe not sufficient. And we can hope for simpler models that could be as expressive, and we could plan better with them, generalize better, engineer the world better. Okay, so the summary for that part is that I really wanted state representations for category level dexterous manipulation. I proposed key points that can represent category level geometry, and we combined that with local sensing and dense reconstruction to complete pretty interesting tasks. And we've seen now that we can learn even the key point dynamics using those ideas. To specify the task, we annotated the key points with semantics in the first set of experiments, but that's human annotation, or we've used self-supervised descriptors with demonstrations. Even for that last experiment where we learned a model, we still required one imitation now in order to say what we wanted it to do, and then it would use the model predictive control to follow that imitation. But I don't mean to say that key points are everything. They're not going to tell you non-geometric stuff, like when the eggs are done cooking. And they don't actually really solve the onion problem. So since I have a few minutes, let me get back to the onion problem. And as much as I like calling it the onion problem, the truth is that Terry realized early on that onions are a bad choice for the lab. They smell bad. They don't show up well on the camera. So I have to start calling it the carrot problem instead. Okay, and giving the robot a big knife and doing all those things wasn't where we wanted to start. So we decided instead to think of the problem of pushing the carrots around once they've been chopped. And that already, that captures the state representation problem I was worried about. And actually the reason we started this was when Terry came to the lab, I was asking him, I said, so can we find the case where feedback from pixels to torques is easy? Like, what is the equivalent of LQR, or linear Gaussian control, or the equivalent of tabular control when we've got a camera? And I didn't have a good answer, but this was the experiment we started to propose to try to dig into that. So the problem here was to find a single policy from pixels to torques that was somehow immune, had no particular concept of the number of carrot pieces. You throw me a different set of carrots down, the same controller works, right? So we're going to define the problem, just move all the carrot pieces to a target set on the cutting board. We're going to do the same thing that a lot of people are doing in these pushing kind of things, parameterize the input as a discrete push, just parameterizing it by the start and end position and assume it moves parallel. The pusher moves parallel to that. And our outputs of the system, our observations, are either images or the vectorized version of images. So, okay, let's try it. Let's just try using images as the state representation. That's, you know, a common thing to propose. It's always made my head hurt a little bit. So we took our original image, processed it down to the board frame, thresholded it, and then turned it into our sort of 32 by 32 representation by downsampling of, that's our image, okay? And can we use that image as our state representation, or the vectorized version of it? Turns out that there's a natural, the control problem here is not that hard, right? So there's sort of a natural control approach, which is look at where all the pieces of carrots are on the board that are not in the set, penalize the distance from those pieces to the set, you know, sum all of those up. And if I can, the interesting idea, you know, of a Lyapunov function here is if I can say that I'm going downhill on that objective, you can think of it like a value function if you're more comfortable with value functions, but somehow just an approximate value function or Lyapunov function says if I'm getting that distance smaller on every push, then I will eventually accomplish the task. And that works. It doesn't require a convex geometry of the target set. It makes some assumptions about making sure that the target set is big enough that the pusher doesn't push things out when you move things in, but it's actually not that much of an assumption. The interesting thing is you can write that Lyapunov function as a linear function of the pixels. That was kind of cool, just by making the image function image, basically, the cost function image, and then convolving it with, or, you know, Hadamard producting with the data image. But to do that control Lyapunov function step, you have to have a prediction of what's going to happen when I take an action in order to pick one that will go down the Lyapunov function well. So we tried Chelsea's deep visual foresight for planning, and it actually worked as advertised beautifully. Very quickly got a network that would start doing the task, but our particular control problem defeated it in a sad way. So it was susceptible to small errors in the prediction. Our Lyapunov function was like horribly susceptible. It just really wanted to push that one caret piece, and there was no sense in which it was going to ever get that caret piece. So it could get in these infinite loops. So we started thinking about, okay, you know, maybe the fundamental problem was that it would either hallucinate caret pieces in the model, or caret pieces would evaporate in the model. It had this idea in that example that it was pushing things in and nothing ever happened. And we were saying, okay, how do you take the deep model and just tell it something about conservation of mass or something? And that doesn't seem insurmountable. But in the process of thinking about how to do that, we said, okay, the frustrating thing is you could actually put that kind of constraint on pretty easily if it was just a linear model. Thought about it a little bit more, and it turns out that actually it's not crazy to think about the way that pixels move in an image, or these caret pixels, as basically for any given push, I'm going to basically do a permutation matrix that will move the pixels from here to here, given a particular push. And yeah, it's not that crazy. So we started to fit large linear models to the data, and they were very easy to fit. You know, we had a standard quadratic programming algorithm. We could put effectively a constraint that says since the elements of y are all positive, this constraint effectively implied that we had conservation of mass. And we got very good predictions out with actually surprisingly not that much data. So considering how many parameters we had. So we'd go from, you know, an example from image ik to ik plus 1. We would learn a linear map that would predict that the carets would all slide from the push up to here. And that was similar to what we were seeing out of the dense visual foresight. And the cool thing is you can introspect. In the linear model, the pixel, the A matrix there is an image. Every row of A is an image, which corresponds to sort of the receptive field of a pixel. So all the places in the image that if pushed, will arrive at that pixel. So you can see the sort of, if I move in the middle frame there, the corresponding kernel, if I move that around, you can see the pre-image of that pixel, and it learns roughly what you'd like it to learn, that pixels that were in the middle of the push end up at the end of the push. What it's not learning is all the coupling dynamics between pixels. But the linear map's perfectly able to think of it as a permutation matrix where all the pixels move independently. Okay, so we put that on the robot. We have a camera off to the side, carrots in the middle, no knife to be seen, and it works surprisingly well. And the little bit of extra work to add those constraints about conservation of mass seemed to make a dramatic difference in practice. Inspired by Lucas and B, we started pushing carrots around adversarially. Okay, I'm not saying that linear models are better than deep models. Clearly they're a subset. This is not gonna work for most problems, but it is, for me, an interesting experiment where we got to find maybe one corner case where really pixels to torque is easy, and we could apply linear modeling, but also linear control to it. So, and the key insight there is that it happened because each of those pixels, effectively, when the carrot pieces are small enough, each of those pixels moves effectively independently. So you can think about the image as a probability density and the dynamics as a transition matrix that's just moving that probability density. And in that special corner case, control becomes easy, pixels to torques. And so we're trying to build back up from that and understand if, I mean, linear breaks down pretty quick, but that gave us a grounding to start from. Okay, so there's many fundamental challenges. I hope I picked, given the audience, some interesting ones on state representation and feedback from pixels, but there's many more that we're thinking hard about, especially the contact mechanics. Let me just show you, one teaser for the tactile work we've been doing to try to understand how the mechanics and sensing of contact can change if you're willing to be soft, and you embed sensors beneath your skin. You can use dot patterns for shear estimation. You can measure contact forces, but you also just have a fundamentally different mechanical interaction with the world. You are touching not with rigid on rigid points, you're touching with patch contacts. You're able to do in-hand pose estimation like this. We're able to do online slip detection. And we're actually able to load the dishes, most of the dishes with the hand. This is an example of something that would be very hard, at a transparent glass would be very hard to see with a vision camera, but it's quite easy to see with a tactile sensor. And I'll finish by saying that I'm trying hard, actually I'm sort of almost without good explanation, working super hard on trying to move my class online, including some of these interactive simulations that are online. You'll be able to run a full simulator, a full manipulation stack directly on Colab. This is just a 3D example of it, but this is a 3D example that if you choose, you can go in and move around, and soon, if you were to log onto Colab, you could teleoperate your robot immediately. We're going to put that online, and I would love for anybody who's interested to visit the class. And the obligatory ending is that we always have to spell MIT in something. So we've got an MIT in the carrots. All right, 258, how'd I do?
Fantastic. Russ, that was stellar. I'm gonna let Peter ask the first question, but there's also a number of great questions in the chat, and I want to encourage everyone to ask questions in the chat. We'll try and get to them as we can. Peter.
So Russ, fantastic talk. Really enjoyed this. Thank you. At the end, you showed the stacking of the wine glasses, and you didn't say much about it. And I got to wonder, how was that done? Was it related to things you presented? What was under the hood there?
Good. So the first thing we did, we actually started that project sort of in parallel. The first thing we did was a more conventional pose estimation tracking type algorithm. We used DART, which is another one of Dieter's algorithms, dense articulated tracking. So, so we are able to do the standard pose estimation pipeline with soft sensors, even in the cases where, see, the tactile is super important because with manipulation, as soon as things get interesting, your hand tends to be in front of your camera, including your sensors. So that added a level of robustness already. But now the big questions are, what's the right state representation that includes tactile feedback? And we're just starting that.
Quick related question, which tactile sensors are you using there?
These are custom tactile sensors. It started with a collaboration with Ted Adelson and GelSight, but this is a large deformation mode version of GelSight, if you will. And the sensor, I mean, you can just put a PicoFlex, a normal depth camera underneath, or you can do projected light and the light, but it opens up more options of what sort of depth reconstruction you do. But the more important thing to us was that it changes the mechanics of contact in a significant way.
Looked a lot softer, yeah. Cool. I'll hand it off to Ken to moderate next questions. Thank you, Russ.
Thanks, Russ. Actually, if you don't mind, could you put and do you have a paper on the linear map that you used? Has that come out yet?
Oh yeah, well, it's sort of out with Wafer. So okay. Wafer's been pushed back, but it's like, yes, it is there.
Oh, okay, great. I'll look up that link while we're talking. I want to say I really appreciate that, because we've had some similar experience recently where we tried something both with deep learning, and then found out that a linear model actually did very comparably. And I think that's a very important lesson for researchers and for students to understand that, we want to often throw these very powerful tools at something, and yet it's very helpful to see the linear model because it's analyzable, as you said. We can start to understand failure modes and uncertainty around it. So I think that is I'm really excited to see the specifics on that. We have some questions from the group, from the audience. Claire Tomlin, in particular, she wanted to know a little more about how the specifics of using key points for MPC. So if you go into a little more detail for her.
Sure. Hi, Claire. Right. So this is the visual prediction. So we're going to take a key point network. Again, we're using the same sort of self-supervised key points. There's an additional trick in that paper of allowing we actually have a large number of key points, because there's to deal with occlusions and the like, and the linear, there's a sort of a linear layer that down selects to the ones that are likely to be unoccluded during a particular experiment on the fly, but mostly it's the same kind of key point dynamics I talked about. And then the network learns a map from the current key point as a quasi-static representation of state, the current action to the next key point. And then how do you unroll that with MPC? That's probably what you're asking, right? So it's hard. It's a mystery to me, really, why people use cross entropy for that problem. I mean, deep networks are differentiable, but the standard go-to is cross entropy. In our experience, it doesn't work super well. And so what Lucas decided he had to pick his battles, he'd focus more on the perceptual thing. And the way we were able to do the planning was by taking the imitation as like the first trajectory, which got us close. And then thinking of the MPC cross entropy approaches as doing a little bit of search around that to find a comparable one. In practice, he would actually roll out a handful of different trajectories and look around them. But I consider that still an open problem of how do you do the planning once you have a model of that complexity, and maybe the wrong problem, but certainly we haven't solved it.
Great, thanks, Russ. Let's see, Roy is asking also a question about Roy Reshef, and if you see it in the chat, he's asking about there's a strong interaction between all the degrees of freedom. Did you consider trying to learn to reconstruct a full distribution over good grasps of an object rather than samples of the key points?
Say it one more time, Ken. I don't have the chat open.
Oh, I'm sorry. He's saying that there are many degrees of freedom with this. Did you consider for grasping the objects? This goes back to the earlier key point work. Do you consider trying to learn to reconstruct a full distribution over good grasps of an object rather than samples of it, actually? Okay.
So the grasping problem, we were trying to be agnostic. There's a lot of good work on grasping, including Ken's. And we felt like we could put any of those into the pipeline to actually do the grasp. And in fact, the one we ended up using in that particular paper was just antipodal grasping. So you take the point cloud and you find some good antipodal points on the point cloud that fit inside your hand. And that was a simple enough heuristic for the problems we were working on. It was more about the problem specification of how do you even talk about what the task is. I think there's lots of room for improvement there and lots of different methods that could plug in, for sure.
Good. I wanted to ask about that too, Russ, because you've made this distinction, between deep models and F equals MA. And I'm curious about if there are opportunity to combine those in some sense with the plate example. It seems like there's a nice Newtonian model of what's going on there, right? You're trying to push at the center of mass and then tilt up at there's a tipping point. And I'm just curious if that could be, had you thought about how those two could be integrated?
Oh, totally. So this is, thank you. This is exactly what I like that problem a lot. I think that it gets more interesting. It's Newtonian mechanics. We have good models of that. They work well. They predict simulations, rollouts well. But the interesting problem is when you have a distribution over plates and uncertainty over those distributions. And are you asking the policy, a fixed policy, to effectively infer a belief and make a decision, which is totally capable of doing? Are you carrying an explicit belief distribution? So I think all of these things are at play, but and I like that problem is simple enough that we can try almost all of them. We can for Claire, we can do Hamilton Jacobian. We can do our sums of squares, and we can do mixed integer optimization on it, and it's like down simple enough for that, at least when in the point finger version. But we can also throw our deep representations, our deep policies at it, or policy search on simpler policies, right? So some of the state machine type representations that C1 used for the dish plate in the first place, can we find that with policy search? All of these are accessible now because the model got simpler.
Great. Okay. I want to ask you also, Russ, about uncertainty. So in some sense, because you showed the representations of the deep dense object descriptors, and you said you were able to reduce the uncertainty very nicely with some recent advances. And I'm curious about actual representation of uncertainty. For example, when a robot would be able to detect when it is sufficiently uncertain to say call for help or just stop motion. Right? How are you thinking about integrating uncertainty measurement into these models?
Awesome question. Yeah. So, we are training those models, of course, with the standard key point approaches, and where you have let's say some blurred radial sort of expected heat map, which has a connotation as uncertainty, and those heat maps do look like a probability distribution over possible objects, but it mixes our training, versus our actual uncertainty about the task. Those are not separated clearly. So we aim, and we do in some places, carry uncertainty all the way through the pipeline. But in that one, it's an opportunity, but not exploited, because I think we're mixing the training performance with the actual uncertainty, ambiguity in the scene. Okay,
great. Russ, we have so many questions for you. I mean, two last questions. One is from Adi Ganapati. He's asking, what are your thoughts on planning in learned latent space representations as an alternative to direct planning with key points?
We went the other way. I mean, we started thinking about the latent space and then asked what's the right latent space. There's something like, just even from an engineering perspective or from a applications perspective, the key points being this this easily understood representation, that they are trained effectively like the latent space, but we're asking them to have an explicit representation in geometry. So I think of it as just binding latent space with geometry so that we can interpret the plans and the results and add semantic tags if we want to. But I completely agree with the philosophy of that.
Thank you, Russ. All right, I think we are out of time, unfortunately, because I wish we could. This is actually one of the most stimulating talks I've heard in the whole summer, I have to say. And I love the way you're thinking about these things and the clarity of the way you present. Thank you so much for using the slides.com. I'm going to try that out myself one time. It's a great way to present a talk. And you've left us with your notes, your class lecture notes for your class, which is super exciting. I'm going to recommend to all my students. And my very last question for you, I want to also thank Peter Beal, because Peter was the one who reached out to you and coordinated this, and he's been very generously hanging in the background, but is really this event would not have happened without Peter. So I want to thank him and also our staff at Bair for putting this together. And my last question to you, Russ, is you may have seen this report about teleshaving from John Peter Whitney, who's at Northeastern. And did you see that article recently?
I know him, but I don't know the shaving. No, I'm sorry.
So
and are you suggesting I should have done something?
Well, the way they put it was he put his whiskers where his mouth is. He basically had postulated that if you really wanted to test this out, you would actually have a robot shaving, and he tried it. And I'll send the video into the link. I'm just curious if you would do the same thing.
Let's see, not with Atlas.
Okay, fair enough. I thought when I saw it, I thought that is a beautiful demo. And
yeah, no, I think we used to joke. Chris Atkinson proposed a metric for walking. You could evaluate how good someone's walking algorithm was by the Atkinson distance. It started off that if people were far away from their robot, that meant that they were confident in their robot. It wasn't likely to fall down. So the greater the distance to the robot meant the robot was probably more mature or more robust. But then Boston Dynamics came around and started using hydraulics and everything. And then it actually became impressive again if you were willing to get close to your robot. So it's an interesting metric.
I agree. I don't know if I'm ready to do it either, but I think it would be a good test for the future to see if who's willing to put their jugular vein on the line there. Okay, thank you so much, Russ. We so much appreciate you making the time and for sharing this with us. We'll look forward to staying in touch with you, and please stay healthy, stay safe. Thank you, everyone, for being here.
You too. Thank you all.
Bye.
Bye.